Hello everyone. In today's session, we will be looking at 10E and 10F. With 10E, it's about sort of definition about absolute maximum and minimum, and 10F will look at problems involving minimums and maximum. So 10F is a little bit more application. This is something that is going to be definitely getting closer to situation when you're not familiar with in that you will encounter in SAC or exam situation. So here let's continue with some of the skills related to differentiation. When we look at a absolute maximum and minimum values, a little bit of the definition that we need to set first. For a continuous function f defined on an interval x is an element from A to B, if f of x is less or equal to a fixed amount m for all that interval for the domain of that function, then m is defined as the absolute maximum value for the function. Now if f of x is above a certain another value for that interval, that is the opposite or the absolute minimum. So here the key terms is absolute. It means that it's over that whole interval. So an example, and we've done the application before, that's why we use the first derivative. When the function is quite complicated, well, you can always obviously graph it, and if you do and you have a set of window properly and you graph trace, those two techniques will allow you to find the minimum and maximum. The general technique is you have your function, you have your over that interval, and it is asking you to find the absolute maximum and minimum value of the function. First, determine if you have a turning point. Depending on the situation, if you have or have not a turning point, then you start looking at the values on the boundaries to find your absolute minimum and maximum. If over that interval I had, for example, a function that was an increasing straight line, because the line will be going upwards from the left to the right. For x equals -3, you will have your absolute minimum, and for x equals +3, it will be your absolute maximum. So the general situation is you determine your turning point, you differentiate, you solve it for that equation equals 0. You find that you have a turning point at x equals 0, which is a 2. Now determine that the type of point that you have. Is it a minimum, maximum, or a point of inflection? So we look at the derivative on the right and the left. So it tells us that it is a maximum turning point. Another way you should know as well, it's a quadratic function. The coefficient in front of x squared is a negative, so it's going to be the inverted shape, so you know you have a the turning point is a maximum. So we have the maximum. Now to find the minimum point, just use the boundaries, okay? Because we find the turning point, it is a maximum, so the minimum will not be at that turning point. So you substitute the values and you find that the minimum has the same amount, so it's at -70. All right, and that will be it. So I think then you can get started with the exercise 10E. Pretty straightforward application. Now if you were to use a CAS, it's not really foolproof, but it's good to know. So plot the graph, make sure you key in the interval for x. You can see that there is a maximum turning point, and make sure you zoom fit, very important to see the entire graph. Okay, the calculator will not set the window to include what you require, so it's up to you to scan the graph accordingly, and then you look for absolute minimum. So here you have your function set, you define your interval with the slash. You can then determine your other minimum maximum by going to analyze graph. You set your before and after. Hang on, zoom fit, yeah. You can also do, then you look for your minimum. Okay, again, for minimum and maximum, you set your lower bound and upper bound, so from the left and the right, that way you can visually guess, and then it will get the exact coordinates. Alright, 10F, which is probably more challenging. It's when you deal with a situation which are problems. So the problems are going to be worded in, you will need to extract the preconditions, determine your variables and constant, and try to find as many relations between your variables. Alright, so some of the steps that you will need to approach. When possible, draw a diagram to illustrate the problem. Anything to do with geometrical shapes, 2D, 3D, do a diagram, annotate it, draw the necessary lines. With geometrical shapes, make sure you don't draw an exceptional situation. If it relates, for example, for me the best example is you relate to a triangle and it doesn't tell you what kind of triangle it is, draw a scalene triangle. Don't force it to be right angle, isosceles, or equilateral, because then it will turn your mind into a specific situation when you think, oh, I have a right angle here, I can use the property of right angle triangle, but you forgot that it wasn't a right angle triangle you started with. As you label the diagram, designate your variables and constant. Be mindful, be consistent with the units as well, and note the value of the variables that it can take. Okay, then moving on, that's how you link all your variables. Write an expression for the quantity that is going to be maximized or minimized, so that's going to be your y or dependent variables. Form an equation for this quantity in terms of a single independent variable, that is your x. And yes, it might require some algebraic manipulation. Then the rest is going to be straightforward. So if y equals f of x is the quantity to be maximized or minimized, so differentiate and find the values of x when the derivative of x, f of x, is equal 0. For each of those values, test that it is a local or a minimum or maximum, or either, because it could be a point of inflection. And if the function y equals f of x is defined on an interval such as a to b or 0 to infinity, check also the values of the function at the endpoint. Even at infinity, you may have an asymptote that is horizontal, and that may give you a local minimum maximum. So typical situation when you have an exponential function, let's say I go with the basic function y equals e of x. The minimum, which is also an absolute, is when x converges towards negative infinity, e of x is equals 0. So that is your local and also absolute minimum. So don't forget just the boundaries of the domain, even if it's an infinity undefined term. Alright, so you can pause this to read the rest, and I'm just going to continue to with the exercise. Alright, now it has 10.5 has a lot of work examples. I'm gonna go through one of them, but there's like 8 of them, so you need to go through it with different contexts, different wording, different situations. Some are geometrical, some may be related to physics, some related to population, and so on. So again, we're trying to apply the steps. The first 2 dot points are probably the ones you need to work out from the work example. The rest is really calculus or algebra. Okay. Alright, so with this situation, it's a geometrical shape. Find the maximum area of a rectangular field that can be enclosed by 100 meters of fencing. Again, I advise you to do a little bit of a diagram. You have the width and the length. Because of the 100-meter fencing, we can express the width and the length in terms of each other, okay, by using the perimeter definition, and we decide to have y, the length, in terms of the width, which is that expression. Then we can express the whole relationship, which is the remember, we try to find the maximum of the area, so we need to express the area. So we have the area is the width times the length. We substitute the length with the other expression, and we get this quadratic expression. From now on, we need to just differentiate, find the value of x, double check that it is a minimum of maximum. It's really good that it is a maximum, so we substitute that value into y well, what we could have done, we don't really need to do that. What we could have done is, with that value of x, we go back to the expression of a, which is that one. We substitute x into the expression of a, and that will give you the final answer. The only reason you substitute the value of x into the y expression if you were required to provide the dimensions. Alright, so another application is, like, we look at minimum and maximum of the function f. Now, what if we want to find the minimum and maximum of the derivative of the function f? What we would use is the second derivative to determine the maximum rate of increase. So the rate of increase is your derivative, and when we say the maximum rate of decrease, is actually the minimum value of the derivative. Okay, so definition of that second derivative is the derivative of the derivative of x, or it is also known as the second derivative of x. It's annotated f with 2 dashes, which is probably the quickest notation for you to do in your workbook. You will also encounter d2 of y over dx squared. Okay, that's the common notation you find in text or references online. In your workbook, just use this notation. So, in terms of language and definition, we define y as the displacement, the velocity is dy over dx, and the acceleration is the derivative of the v, which is the velocity, so it's dv over dx, or d squared of y in terms of dx squared. So just the key terms here is, as you differentiate, your function is your displacement, you differentiate, you get what we call the velocity, you differentiate again, and you get what we call the acceleration. So let's look at maximum and minimum of rate of change. So let's say you have a population or a function n in terms of time, which is has a linear factor and an exponent, a decay. Sketch it, just use a CAS. Differentiate, you should be able to differentiate using a product rule, and you can also use a CAS to graph it. Wait, let me pause that, I'm missing the graph. Alright, we're back. So here are the graphs. So you get a sort of exponential increase. It peaks up here and then decays down back to 0. So you have an asymptote here, and then when you differentiate using a product rule, you get that function that goes all the way down. So remember, that's the derivative. It decreases down to this value and start increasing again back to getting close to 0 from below. All right. So to find the maximum rate of increase and decrease of the population and the times at which is occur. Now, so we have that function. That's our derivative here. We're going to call it r of t. From the graph, you can see here that's the highest value, and it happens at the y-intercept. So it's when t equals 0. So the maximum rate of increase of the population is 36. So that's the value you read. Now remember, it's the derivative, so it's the number of bacteria per unit of time. It's a rate of change. Now we want to determine that lowest value, that minimal rate of increase. So to do that, it's a turning point on that function r. So we differentiate r and we solve it for t when we make it equal 0. That gives us t equals 20. We don't need to look to investigate if it's a minimum or maximum. You can see from the graph it's a lower value. So when you substitute t equals 20, r of 20 or n prime of 20 is going to be approximately negative 4.9, which is bacteria per unit of time. So the way you rephrase it, that's a negative value, but what we do is we take the modulus, so we take that value of 4.9, and in the sentence we re-express it as it's still a maximum rate of, what's changing is the decrease. So it's a maximum rate of decrease of the population is 4.9 bacteria per unit of time. And that's it for today. See ya.